Today we will discuss thermodynamic properties of an ideal but diatomic gas. An ideal diatomic gas basically has translational, rotational, vibrational and electronic energies. Okay, so we can write the molecular partition function for a diatomic gas equal to the product of these partition functions, that is translational partition function, rotational partition function, vibrational partition function and electronic partition function. But out of these we have already discussed the translational partition function here and the electronic partition function contributions to this molecular partition function while discussing the thermodynamic properties of a monoatomic ideal gas. Okay, so that means we will simply focus on these because we have already discussed these two. So we will discuss on rotational and vibrational partition function for a diatomic ideal gas. Okay. So first we have to know that the internal energy but rotational internal energy we will write it as equal to, as we have already derived this relation, RT square dou upon dou T ln of Q rotational. So we will put simply the value of Q rotational here. So Q rotational will be equal to, we know it is related to by this expression 8 pi square I kT upon sigma h square. Here you have to remember that this sigma here, it is basically symmetry number. So suppose you have a diatomic molecule. By only rotating a molecule, how many identical configurations you will get? That will be simply equal to this symmetry number. So it has been observed that this sigma, which is symmetry number, if you consider first a homomolecular diatomic molecule, for example hydrogen molecule, oxygen molecule, nitrogen molecule or any, but that should be homomolecular diatomic molecule. That means then in that case sigma is simply equal to 2. And for a heteromolecular diatomic molecule, for example if we have carbon monoxide NO or hydrogen and deuterium HD, or you can take example of HCl also. In these cases this sigma is, that means this symmetry number is equal to 1. So in short, you have to remember, if you have a homomolecular diatomic molecule, sigma will be equal to 2, and if you have a heteromolecular diatomic molecule, sigma will be 1. We also know this Q rotational here, we can write it this in various other forms also. Suppose we can write it equal to T upon sigma theta rotation. How? We know this characteristic rotational temperature, it is basically equal to T upon rotational partition function. So we have already discussed this in the rotational partition function. So from that we will get this relation. Or one more form of this relation is that, suppose you can write this rotational partition function as kt upon sigma hcp. Here this b, which is simply called the rotational constant, it is equal to, that means this b will be simply equal to h upon 8 pi square ic. C is simply the velocity of light, and h is Planck's constant, sigma is here symmetry number, k is Boltzmann is constant, and T is absolute temperature. Okay, so these are some of the various forms of this relation. So we will focus on this relation here, that means the rotational internal energy. We will write it as RT square dou upon dou T ln of Q rotational. So we will put the value of Q rotational here, that means Q rotational, which is equal to I have given in the above equation, but I will write one more time here, IKT 8 pi square IKT upon sigma h square. Okay, so simply we will put the value of second in first. So we can write the rotational internal energy will be equal to R T square, and we can break this into two parts. It is with respect to temperature, so all other terms except temperature, if you focus on these things, this will be simply a constant. So we can write it as dou upon dou T of, and this is ln here, so we will write ln, and first this part, that means 8 pi square ik upon sigma h square, and plus dou upon dou T of simply ln of T. RT square is multiplied to both terms, and differential of this constant, this will be simply equal to 0. So we will get a very simplified relation here, that means internal energy rotation will be equal to first to this part, RT square multiplied by this part, we know differential of ln of t will be simply equal to 1 upon t. So we will write up in this way, 1t. So one of the t's will cancel, this and this. That means we will get the rotational internal energy will be simply equal to RT. So remember this relation. This is very simple relation, and it has been asked many times in different exams. Okay, now if we have derived this rotational internal energy, then we can define or derive the relation for specific heat capacity at constant volume. But for this rotational part, that means rotational partition function, we can write it as this is differential of internal energy with respect to temperature but at constant volume. Okay, so we will simply put the value of u here, RT. So we can write dou upon dou T RT. So it will be simply equal to R is a constant, it will be outside, dou T upon dou T will be equal to 1. So we got this relation. So now we can derive one more quantity, that is the entropy, but for this rotational case. Okay, rotational entropy you can say. So we know this is basically related by this expression, internal energy upon T plus R ln of Q, or we can simply write for understanding here internal energy rotation. Okay, subscript. Okay, then Q also Q rotation. So we already derived this. The internal energy is basically equal to here RT. We will write the value here, RT upon T, T is here, plus R ln of the rotational partition function, which is for a diatomic molecule equal to 8 pi square IKT upon sigma h square. Okay, so here this temperature and T will cancel, so we can also take out the R common from these two terms, so it will remain here 1 plus ln of 8 pi square IKT upon sigma h square. So this will be our rotational entropy. Okay, this is the equation for this case. Okay, now for vibrational partition function, we know Q vibrational is related by this expression, 1 upon 1 minus, we will write the final equation here, e raised power minus h nu upon kT. Okay, or in terms of vibrational characteristic, vibrational temperature, we know this that the theta vibrational is basically related by this expression h nu upon k. Okay, so we can put the value of theta at vibrational in place of h nu upon t, so it will be 1 upon 1 minus e raised power minus theta vibrational upon, so simply t. Okay. So this can be written in this form also. That means we can now derive the relation for vibrational internal energy. So we will again write the case, the relation in terms of partition function. The internal energy is related by RT square dou upon dou T ln of Q, but here vibrational partition function. So it will be equal to RT square dou upon dou T ln of 1 minus, so you can write this in one more form. If you take this denominator to numerator, you can write simply 1 minus e raised power minus theta vibrational upon T whole power minus 1. So we will simply introduce this value here. It will be 1 minus exponential over minus theta vibration upon T whole power minus 1. So you can take this as log m raised power n here. So we can solve this RT square. So it will be first minus 1 and then simply dou upon dou T ln of 1 minus exponential to the power theta vibration upon T. Okay, so this minus you can write in front of this RT square. But one more point you have to remember here is that if you have a differential like this one, dou upon dou T ln of Q, we can write it as 1 upon Q dou Q upon dou T. Or if you have this kind of differential, you can write this in this form also. So if we apply this here, it is ln of, suppose take it as Q, so it will be 1 upon this Q dou Q upon dou T. So we will simply write it as in this form also. Here it is minus, we will write it before RT square minus RT square, and we will multiply. So this is 1 minus e raised power, that means 1 upon Q, we will write it 1 upon 1 minus e raised power minus theta vibration upon T, so it is into dou upon dou T into 1 minus e raised power minus theta vibration upon T. So simply we have used this in the above in ln of q, and differential of ln of q will be equal to simply this much. Okay, so this will be our equation for this vibrational internal energy. So we can simplify this part here. If we take this part, we can write it as, I will write here, it will be equal to, I am only solving this part, it will be equal to so it is a differential of 1, that will be 0, but differential of exponential e raised power minus x, like that. So I can write is minus e raised power minus theta vibration for t into differential of function, which will be simply equal to theta vibration into 1 upon t square. That means this is differential of function theta vibration upon t, which will be equal to theta vibration, we will take it out, and with respect to t raised power minus 1 we will differentiate, that will be equal to t raised power 2 and this minus here. So you can further write this as this. First we will write minus, here we will use a simple relation here. We can write minus theta vibration upon t equal to theta vibration into 1 minus divided by t. Okay, so this is simply, we will use this also here in this relation. So our relation will now become the total relation. Here this is minus RT square. First we will write that minus RT square into 1 upon this part, we will write it as such, 1 upon 1 minus e raised power theta vibration upon t into this part here. That means we can write minus into e raised power minus theta vibration upon t into theta vibration upon t square. Or we can use this one and we can write this part in this form also. So that means we can write it here. First we will cancel one term here, that means this t square and t square, this will go. So we will write, and this minus and this minus, it will be plus. Okay, so we will have this relation now, r multiplied by this much, 1 upon 1 minus e raised power minus theta vibration upon t into, I'm talking about this one, we will use this analogy here. We can write it as e raised power minus theta vibration upon T into theta vibration. So our equation becomes R. First we will write this part here. It will be theta vibration, and this part e raised power minus theta vibration upon T whole divided by this term. That means 1 minus e raised power minus theta vibration upon T. So we will multiply these terms. So this will be our vibrational internal energy. Now if we put here this theta vibration upon T equal to x, so we can simplify this relation here. We can write the vibrational internal energy basically equal to R so in place of theta vibration we will write here theta vibration will be then equal to x into T. Okay, so we will introduce here the value in place of theta vibration as Tx or xt, and it is exponential, and we have put this value equal to theta vibration upon T equal to x, so we will write it minus x and upon 1 minus e raised power minus x. So further this we will further write here point that this 1 upon 1 minus e raised power minus x can also be written as 1 upon 1 minus 1 upon e raised power x. This is very simple, so we will simply cross multiply. That means it will be 1 upon 1. So this can be then written as that means we can write it as e raised power x upon e raised power x minus 1. So we can put the value in place of here. So internal energy, vibrational internal energy will be equal to RTX into e raised power minus x is here, and in place of this part we will introduce this part. That means multiplied by e raised power x upon e raised power x minus 1. Okay, so this and this will go, it will be equal to R dx upon e raised power x minus 1. That means this will be our vibrational internal. Or we can put the value of x is equal to theta upon T back, so we will get RT, and in place of this we can write theta vibration upon T whole divided by e raised power theta vibration upon T minus 1. So this equation can be also written in this form. Okay, thank you.